Right. All right. Hello, everyone. Let's get started. Okay. I finished grading your exam, so you can check the grades. They're posted on Brightspace. And then I think you have one homework assignment, right? That's due this week. All right. This is now week 7, so we're starting like the second third of the semester. And in the first third, we focus on symmetric encryption, block ciphers. We're still going to be using those, obviously, to achieve confidentiality. But now we're going to focus on asymmetric encryption. So if you remember the problem of exchanging the key securely. And this is very interesting how we're going to do this. So here in asymmetric encryption, there's going to be several algorithms, starting with RSA. That's the classic, still in use algorithm. There's also going to be elliptic curves, which is another one very powerful, modern technique that's used in some examples, for instance, of the blockchain, things like that. You'll have that. So elliptic curves will be another one, but to understand, but elliptic curves is related to RSA, right? So understanding RSA first um, will help you out to understand elliptic curves. So that's what we're going to do today. We're just going to look at RSA, the RSA algorithm. I'll motivate it. This is, I would say, really nice algorithm. It's based on, it's more mathy probably, but it's based on algebra. So essentially, high school algebra is about all you need for this. So it's really interesting. All right, so you have to think of it as people used mathematics and then they figured out, hey, you know what? If we do this, we're actually able to build, this infrastructure for key exchange. Okay, so let's take a look. I'll motivate the materials today, the modules, where we are. There will be a homework assignment this Thursday, a new one related to RSA. As you might imagine, we'll just start implementing RSA, essentially, the RSA algorithms. We'll do several implementations of it, and there's several steps to it, but I think it's very interesting, right? And again, once again, just like before, the algorithms are very well known, and the security just depends on the math behind it, and also keeping the keys secure. All right, so let's take a look at our folder here. I'm going to go to content. I'm going to go to table of contents. All right, so we've covered all of these modules, hash functions, XOR and symmetric encryption, exam 1. This was the last thing we covered. And now we have a new sequence of topics that we need to cover, which is asymmetric encryption and RSA. PyCrypto is just a library, so I'm going to introduce a more powerful Python library that we will be using for a lot of the things that we need to do. So it's going to get very you're going to have to encrypt a lot of things now going forward, right? So achieve confidentiality, integrity, authentication, etc. So we need to explore all of these ideas. And then that's going to take us to even more advanced cryptography, such as certificate authorities and digital signatures. Okay. And then that'll take us to about the exam number 2, where the final third of the semester is essentially more on the application side. So the application of a lot of these cryptographic techniques. So for instance, for malware, denial of service attack, blockchain and cryptocurrencies, things like that, and a few last topics. All right. Oh yeah, this one, PKI, it's an implementation of like HTTPS. So that's another application. All right, so let's take a look at this one here. This is our module for this week. So I have some reading here. This is just for you guys to read, kind of for fun, quantum and crypto. So this should be a really nice article, Keeping Secrets in a Quantum World. So again, I don't know if you heard in the news, three people won the Nobel Prize in Physics for quantum computing. So obviously, when you see Nobel Prizes, it means that the things are starting to make it into application. Okay, so maybe we're getting closer to quantum computers. I don't know. But certainly you can infer something from that. So read this article. I'm not going to have questions about this on the exam or anything like that. This is just for you guys to read it, but it's a very nice article. It's a type of popular science, just talking about how quantum algorithms could break cryptography in the future. So that's really what it's about. So just to see what they're doing as far as developing new algorithms and what's the state of the art in this field. I'm not, this is from 2023, so certainly there have been some developments since then, but just, keeping our eye on quantum and crypto, right? Something to worry about. So if quantum computing became a thing, there might be a cryptography number two, right? And that'd be the quantum version or something like that. Also, as I've said many times, for the term project for this class, that's a nice topic to research, right? So if you guys want to research quantum computing algorithm, Shor's algorithm, uh, all the other ones, you can do that. Certainly, students have done that in the past. All right, so we are here in this module. So there's the quantum and crypto. We're going to have, this is my PDF, my notes that I'll do. I'll use the whiteboard today, and we'll go over the algorithm essentially of RSA and get a feel for it. Got some slides also. I'll cover these at some point, more of a summary of the topics we're covering. Okay, this is a Python script. This is also on the GitHub that we're going to be using for the lab. And then there's going to be the homework assignment. Okay, so let's take a look at this document, RSA homework, and it'll just motivate what we're going to be doing, right? And how what I'm doing on the whiteboard relates to your homework assignment. Essentially, remember the two things that we're doing here. The idea with asymmetric encryption is we're trying to do key exchange, right? So it's not about encrypting that Netflix movie that you're downloading, right? So to encrypt that movie, we would still use AES. Okay, that should be clear. That's the fastest way. We know it's pretty secure, all of those things. But as you know, you have the problem that you need to exchange the AES key. And so for that, we're going to need an asymmetric encryption framework. And as it turns out, asymmetric encryption frameworks also have other applications beyond just exchanging keys. So that's where like digital signatures, contracts, and things like that come into play. And we will see that. Okay. But anyway, so you can see here the problem. So this is, some of the problems that we're going to do. Problem one, just implement a very basic toy type of implementation of RSA. We're going to do some problems, and you're going to implement this in Python. And then we're going to just scale it up, right? So I'm going to start with a very basic example of how RSA works, and then we're going to start adding more realistic parts to it until we actually arrive at a very complete implementation of the RSA algorithm. So you'll be able to see it, in from scratch in full. And then as you can see, you'll have the traditional problem of, using the code from problem three plus any symmetric encryption approach, send a message to your partner and achieve confidentiality. This time you must exchange the symmetric key securely. So this is the first time, right? So on week one, I asked you to do this. You were not able to do it. Now on week seven, you are able to have full security because you're going to exchange the key first. But you're going to be working with your partner, and this is where working with a partner makes it harder, right? Because now RSA is going to involve having so many keys, right? Everyone needs to have what? two asymmetric keys, the public and the private key, right? So you need to know which ones you're supposed to use. And then you're going to be using those algorithms to encrypt the symmetric key. That's another key. And you're going to send that, right? And then you're going to use that key to encrypt the message. And I could ask you to achieve integrity, confidentiality, and so on. So you can see how it starts to, we have way more things, way more moving parts. So you want to be organized with this one, right? Remember saving things to files and things like that. But anyway, this will be the lab that we will do. We'll start with problem one. I usually like to start with the homework to motivate. So I might start doing some of these today. So especially problem one, we'll implement this in Python and so on. Okay, so we went over that. I think these are just my notes from today. Yeah, so this will be just the notes that I'll cover, so you have that available to you. This PDF. Yeah, this is more notes and examples, so you can have those as reference, and I'll cover those on the whiteboard. This is the slides. I'm not going to cover the slides today. This is the Python script, so we'll get to this one also, and it's a very nice one. A lot of these things also remember you're going to need for the scavenger hunt, right? So remember that on week 12, around week 12, we will have a full lab session just dedicated to the scavenger hunt. And what I usually do there is I encrypt the secret message, but you have to retrieve several keys that have also been encrypted, right? So it's a combination of several. So I'm using different techniques for each one, and these are the scripts that you will be using. Okay, so at the heart of that, one of the key things you'll have to do is break RSA in a very simple way. All right, so you need to understand this algorithm here is essential for that specific part of the problem. Okay? All right, any questions on that? Yeah, so keep in mind, so we'll have homework assignments, obviously, from now until week 12. Around week 12, we will have a written exam, pretty much like exam one, which will be exam two, and then we will have the scavenger hunt either that Thursday or the following Thursday. So mark your calendar for that. Okay? And it should be fun. So some students break it in 15 minutes. Others don't break it, right? So it's not really about, it doesn't take long, but you really have to understand what's going on. All right. Yeah, so should be a fun exercise. So let's get started then with the notes in RSA. So I'm going to switch to the whiteboard. And this is, essentially this is about solving problems and understanding how this works. All right, so RSA is the topic. RSA, there's another algorithm actually that we will cover also. So Diffie-Hellman. And we'll cover Diffie-Hellman as well. So there's a story, there's like a history here, right? So around the 70s or so, people were encrypting things, but they needed to exchange the key, right? So there was this problem. So how do we solve this? And so we have people like Diffie and Hellman, who were I think they were professors at a university. They were just working on this as research, doing math and trying to figure out how to securely exchange the key. And they kind of arrived at the main idea. Like they created like this concept that they're like, I think if we take this approach, we can do this, right? So they proposed a technique, Diffie-Hellman. So that's going to be one of the ones we cover later. Although historically Diffie-Hellman was first, I usually start with RSA and we'll dive into Diffie-Hellman later. Okay. Yeah, and then there was this call to implement that as a full algorithm. So many people answered the call, and then these three researchers here by their names, RSA, created an algorithm, and they called it RSA, and it was chosen as the best algorithm for this task. And then since its invention, they've had a conference every year where they try to break this algorithm, etc. And they're still, as far as we know, unable to break it. Now, obviously, if the keys are very small, you can break it, right? But so a lot of the security depends on the keys being very big, very large. And you guys will see that they are, in fact, pretty large. But yeah, so that's kind of the history of this. Okay. So the RSA is a cryptographic algorithm which was developed by three researchers, Ron Rivest, Adi Shamir, and Leonard Edelman at MIT. Okay, so that's where the name comes from. It's from their names. So, so the algorithm was developed around 1977. So it was developed around 1977. Okay. And it's still in use today, although we also have the second option called elliptic curves now, which obviously is more recent. Now, RSA uses both public and private keys, right? So that's going to be another feature. So now you're going to have a public and a private key. So every person will have one of these. You know, Bob has a public and a private key. Alice has a public and a private key. Now, the public key is known by everyone, and the private key is kept secret. Okay, so that's really important. They go together. They're essentially a pair. So you can think of it as you first generate the public key, and then from the public key you generate the private key. So the private key might be using a function with the public key. So you generate one from the other. So that's one of the things that we will explore today. So what are the rules for this? Okay. Now, a message encrypted with the public key can only be decrypted with the corresponding private key. Okay. All right. So the first thing we're going to look at is the steps to RSA. So the way I usually do this, because it's got a lot of details, is that first I start at a very high overview of it version. And so we'll just look at some of the steps where I'll simplify a few things. And then as we start to understand it better, I will, add some of the things that I'm removing initially. Okay. And this is just so that we can make it more accessible. Okay. All right. So let me then talk about the general steps of RSA. So these are going to be the steps of RSA. Okay. So the first thing that we're going to need is so let's say step one, we need to generate two random and independent large prime numbers. Okay, so that's the first thing we're going to generate. So you guys know what prime numbers are, right? Anyone want to give me a definition of a prime number?
Number.
Yeah, exactly, right? So you guys done this is very fun. A lot of people study this, like what are prime numbers? There's no real pattern in how they work, right? So it's like there's a prime number and then another one, and then 100 steps later, another one, and then so no one has been able to figure out why that happens in nature, but yeah. So here we are going to need a function to generate prime numbers. So luckily Python provides such a thing. So we will have a function that can give us prime numbers. But initially I can just, in the first few examples, I'm going to pick very small numbers just so that we understand what's going on. Obviously, so 3, 5, But as we start to move on, you need to understand these are actually really large, right? It's very large. But that's the start of the process, okay? So the first step is pick two prime numbers, and we're going to denote them as P and Q. Okay, so these are going to be your prime numbers. So select two large prime numbers. Okay, so P and Q. Given those numbers, we are going to calculate a value n, which is sometimes called a modulus. So let's just say step 2 is calculate n, where n is actually equal to P times Q. Do you see that? So this is a very important part of the algorithm. As it turns out, this is how you break RSA in theory. Okay. So if you were able to reverse this process, you would be able to break RSA. So what do I mean by that? N is actually something that you're going to see. It's part of the public key. So an attacker can have access to N, and if they just had some kind of a magic algorithm, etc., they could, look at N and somehow figure out, oh yeah, N is essentially, if I take P times Q, I get N. Do you see that? So that's essentially how you break it. So the security of RSA depends on the fact that doing this is very easy, but doing this is very hard, especially for really large prime numbers. Okay? So this is going to come into play later on in the following weeks as we start to dive deeper into RSA and try to understand it and essentially break it, as you guys will try to do later. But for now, we're just going to think of this as we are going forward. Okay, so essentially the two prime numbers, yeah. This is times, so P times Q gives you N, and that's step number 3. Okay. And like I said, in this initial discussion, I will just say I might say like, we have to meet this and also these other additional conditions, and we will discuss these additional conditions a little later. All right, so in this first step, we calculate N, which is the product of P and Q. All right, step number 3, now we need to calculate another term called, this one is called phi. So calculate a function phi, which is the product of P minus 1 and Q minus 1. So we're going to calculate, sometimes this is denoted like this, okay? The symbol of the Greek letter. Or we can just use phi and the code, we'll just write phi. And this is going to be P minus 1 times Q minus 1. Okay, and that is essentially step 3. So if you notice, we just start with a few prime numbers, we start creating these variables, and then we're going to be using these variables to make, to pick numbers, essentially, and these are just to create the public and the private key. So essentially, a lot of these steps are to create the public and the private key. All right. So that was step 3. We've calculated phi, and it's just P minus 1 times Q minus 1. Now we can move on to step number 4. Step number 4. So here I'll just kind of write this out. So select a value E such that we meet the following condition. So E is greater than 1 and less than phi. So that's one of the conditions, okay? Which is phi is the previous term that we just calculated, okay? And for now, I'm just going to say, and it meets a few additional conditions, right? So select a value E such that this is met and, oops, and it meets few other conditions. So we've got this other condition that we'll talk about later that E must be co-prime with phi. All right, so we'll need to like elaborate on what that means. So we'll do that later. Right? But for now, let's just say that that's what it is. So select an integer E such that it meets that condition. It's less than phi, between 1 and phi, and also the E meets a few other conditions. This E term is really important. So E is really important, and it's going to be called the encryption exponent. The encryption exponent. So in fact, this E is going to be part of the public key. At this point, actually, we have the public key. So the public key is a tuple of two values. And we will see this later when we go to OpenSSL. I have a few commands so that in OpenSSL, when we look at a public key or a private key, we can actually see exactly what it's made of. And we will see that a public key is in fact a tuple of two values, where these two values are E, comma, N. Do you guys see that? So this is really important because what is N? What did I say N was? N is the product of two prime numbers, right? Two very large prime numbers. And I have also stated that the public key is shared with everyone. Therefore, if you're an attacker, a hacker, whatever, you see the E and you see the N. So you can immediately start, attacking N and trying to figure out, okay, what two prime numbers generated this? Okay. So you know that both N and phi are based on those two prime numbers. So that's essentially, one of the, not a weakness, but that's the attack vector, as I guess I should say. Anyway, at this point, we have created the public key, and it is a tuple of E and N. Okay, so we have that established. All right, so we can move on then to step number 5 of the algorithm, which is the step where we want to find D. And D is going to be known as the decryption exponent. Going to be the decryption exponent. Okay, so we have to figure out how to calculate this. So to calculate D, we use a formula. So the formula is going to be, and it's really more of an algorithm. So it's a kind of a thing that you have to do. You have to kind of try to figure out what matches this condition. So you're going to have a formula D times E mod, and this mod is an operation called the modulus operation. So in Python, you may have, or in another class, you may have looked at this. In Python, this is going to be this symbol, the percentage symbol. So you'll see this in the code. And this is the operation. So D times E modulus phi has to match, this is the equal sign, 1. Okay. So as I said, this is an algorithm that we have to use that has to iteratively figure out and break this parameter. So if you look here, we have already E, right? This is a value that we already figured out. We got phi also. This is just a 1 and this is an operation. So basically we have everything that we need to solve for D. Okay, so that's essentially the idea. So to calculate D, we're going to solve that equation. So once we have that, once we figure out D, we can write our private key as D comma N. So the private key is essentially the same, it's a tuple just like the previous one with the same N, but it's got a different exponent, which is D. Now that E and D are going to be different in size. Usually E is much smaller, whereas the D exponent is very large as well. So the public key is the combination of N and E, and the private key is the combination of N and D. So at this point, we can say that, you've established this whole process was just to generate the public and the private key. So here, if I have Bob, for instance, then Bob has a public key, and Bob's public key is going to be E comma N, and then Bob's private key is going to be D comma N. All right, so you've actually established the keys. You make this one available to everyone, so everyone can use this one. And then obviously Bob keeps this one private. All right, and so now you have a mechanism between Bob and Alice to be able to share a symmetric key, such as an AES key. Now this is just to generate the key. So this is the generating function. We still have to do the encryption, right? So now comes the part where we're going to use these keys to encrypt something and also to decrypt it, okay? And like I said, it's all based on the same math here. So we're going to go ahead to the next page. And now we want to encrypt something. So let's imagine an experiment where we have Bob and Alice. Alice wants to communicate with Bob and send a key, like a secret key. All right, so how does this work? Or let's say Bob. So Bob wants to communicate with Alice. He wants to send her a message M. Bob knows the public key of Alice, which is N comma E. So now Bob encrypts the message M using Alice's public key. Okay. So that's essentially what we're going to try to do. So we need two functions for this. We need the encryption function and the decryption function. So this is going to be encryption for RSA. And then also the decryption. Or RSA. And the functions are actually pretty simple, which is great, right? So they're not bad. So we have here, we also established that the plain text message is M, okay? So in this case, let's just keep it simple. Let's say it's just a number like, 25, something like that. Just keep it simple. And then later on, we're going to see how we can actually do this with something longer, because obviously a string has to be converted into numbers and all of that. But so the encryption formula is C equal M to the E mod N. Do you guys see that? That's it. That's the encryption formula. So you take, Bob wants to encrypt, right, his message and send it to Alice. So Bob is going to need what? Alice's public key. So this E and this N have to come from Alice's public key, okay? And then this will produce C, okay? Which is what? The cipher, right? So this is the cipher. Then we're going to decrypt the message. So now let's say that Alice has now received the message and she's going to decrypt it. So what is she going to use? She's going to use her private key. All right. So in this case, the equation for decryption is very similar. So it's going to be M equal C to the D mod N. Do you guys see that? And that's it. That's RSA. There's a few other steps, like I said, like when I did that whole and a few additional conditions, things like that. There's going to be a lot of helper functions to go from string to integers, etc. But essentially, this is the whole algorithm, right? So pretty impressive. That is such a simple algorithm. It's just a little bit of algebra. All right, so Alice receives the ciphertext C from Bob. Alice uses her private key to decrypt the ciphertext to give her the original message back, M. Okay, and so you can see that oops, this just uses D and N from her private key, essentially. All right, any questions? Pretty simple, right? It's amazing that this little set of equations are used every day, right? And we are able to think about it, do banking, Netflix, Brightspace, your cars for some of you, right? And all thanks to this, just a few calculations, right? So yeah, this is the algorithm. All right, so hopefully that made sense. We're just gonna spend a few weeks on looking at this algorithm. We're gonna look at we're going to add more components to it and convert it obviously into Python code from scratch for at least for the next couple of weeks. All right, so the next thing I'm going to do is I'm going to actually add some numbers here, and we're going to start doing this as a problem. So work out the problem, and then from there, we're going to try to implement it in Python. All right, so let's assume now a simple example. And just keep in mind, so I'll do several of these, for the next few weeks, and there will be some problems like these on the exam. Okay. All right, so let's do a problem now. Simple example, let's call it. Simple RSA example to drive the point a little bit more. Simple RSA example. Okay. All right, so let's start. Let's choose. So let's follow the steps, right? So the first step is we have to choose two random prime numbers. So in this case, I'm going to pick P and Q to be equal to 5 and 3. So 5 and 3. So these are prime numbers. Okay. Now pay attention to this problem also because there's going to be a weakness in it. There's going to be something that, that shouldn't happen with RSA, right? So let's see if you can spot it. All right, but take a look. All right, so let's see if we're following all the rules and if the algorithm is fully secure. So we have step one, P and Q, two prime numbers, and we agree that 5 and 3 are, in fact, prime numbers. The next step is to compute the value N. So that's going to be N equal P times Q. Okay? So this is going to be 5 times 3, and that should be 15. So we have now calculated N to be 15. All right. Now, here I'm going to simplify this part a little bit because I haven't yet given you how to calculate the constraints of E, but let's just look at this part. So I need to select an E that at least is somewhere between 1 and phi. Right? So in this case, phi is 15. Okay? So I need to figure out a number. And this step, a couple of these steps actually require an algorithm to figure it out. So it has to try several things until it finds something that meets the condition. Yeah.
I thought B was equal to E minus 1 times Q minus.
Oh, that's right. Did I skip sorry, I skipped a step. You're right. Good point. So I jumped ahead. So let's say this is 3 and this is going to be 4. Sorry about that. Good catch though. Yeah, so 3, I need to calculate phi, which I haven't done so. So what is phi actually? P minus 1 times Q minus 1? Yep. All right, so P minus 1 times Q minus 1. And that should be what? 4 times 2, correct? So 4. So it's 5 minus 1, 4. And 3 minus 1, 2. So that's going to be 8. Okay? Yeah, very good. So now we want to look for a value. So not 15 then. Because that's n. So phi would be 8, right? And now we have to pick this value, plus we have to, the other constraint is that we use something called a GCD. So we'll look at this later, right? But we need to do a comparison. The greatest common divisor, right? So something that you probably looked at in high school as well before. So this is another algorithm that we have to apply, and we examine the values E and phi, and we're going to pick one that meets conditions related to this. But for now, I'm going to skip it, and we're just going to say that E then is going to be 3, let's just say. Okay, these are very small numbers, so we don't really have that much room here, but it's just an example to get started with. And definitely later on, this is going to be much more complex. All right, so that's E is equal to 3, right? So we know at least it meets this condition that is between 1 and 8, where 8 is phi. Got it? All right, so let's move on to the next step. And now we should have also the public key, right? So we know that the public key for this person, let's say that this is Bob, okay? So the public key is n comma E, which means that it is 15 comma 3. Do you guys see that? Any questions about this? Nope. All right, great. So now let's move on to step number 5. So we have the public key. What do we want to do? We already calculated E. Now we want to calculate D. Right? We need to know what D is. And we said that it needs to meet the condition that is E times D mod. What was it? You guys remember? Was it phi? Let me make sure I'm not. Phi equal 1. All right, so I will do an exercise, a separate exercise on how to calculate this, because this actually takes a little bit in the calculation, okay? But I'll demonstrate that in a second. So here we know we have E. So what was E? 3, I think. We had 3. We don't know this one. We know that this is the modulus operation. This phi was 8, I believe, equal 1. Do you see that? So we just have to, we have all the values, and we just have to kind of solve for D, right, via an algorithm. But let's just say for now that we have the algorithm, we have solved it. So D is going to be, in this case, let's say it's equal to 3. Okay, so now my private key, or Bob's private key, is what? N comma D. So that would be 15 comma 3. Okay? And so that's the private, and then the public key is public key. is going to be n comma e, which is 15 comma 3. All right, so you can probably spot that there's a problem here, right? This shouldn't happen. So this is a very simple example, the only one where these are going to match. Going forward, they're not going to match, obviously. All right, but we're going to, I usually like to start here just to point that out, that they shouldn't match at all. All right. And yeah, so we did that before. It was 3 over here. Okay, make sense? All right, so now that I have these, just to illustrate the simple example, let's proceed to do the next calculation. So at this point, you've built a function that allows you to generate your private and your public key. Okay, so the next step is what? Now you're going to proceed to do the encryption. Okay, so if you notice, what I'm doing right now is actually problem 1 of the homework, right? So this is the first problem that we're going to solve. With Python from scratch, you're going to do this exact same encryption, and you should get the same values that I'm getting here by hand. And, then we're going to try a more correct set of numbers that's going to just to further illustrate. All right, so now that I have this, I'm going to move on to the encryption and the decryption. So we're going to say that my plain text message that I'm trying to encrypt is the number 7. So this is what I'm going to try to encrypt. So I'm going to have, once again, my encrypt and decrypt functions. So we've already wrote these down, right? So we know that to encrypt the message, so I have the cipher. So obviously I have a plain text message. So the equation is m to the e, right? Mod, and then what was it? N, correct? N. So that's it. So that's how you encrypt. So then we have C should be 7, E was 3 to the 3, mod 15, right? And if we, in this calculation, we're also going to have to do it in Python, right? So we'll do this computation in Python, but it should be equal to 343. So you can corroborate that. Okay. All right. So it should be, no, sorry. 343 is this. 7 to the 3 is 343. So let me actually erase this. We'll double check in a sec, but see. So there's 7 to the 3. And if you guys have a calculator or something like that, you can try it out. It should be 7 to the 3 is 343 mod 15, and that should be equal to 13. So the cipher here should be 13. All right. Any questions? No? All right. So that was the encryption part. So let me in parallel now just add the decryption part on the right. So here I'm going to do decrypt, right? So now let's say Bob sends 13 to Alice, right? Remember that this is just what? This is the secret AES key, for instance, right? So this is just the AES key that you're going to use in your symmetric encryption algorithm, AES, DES, that kind of thing. All right, so now you're going to decrypt. So we're going to use the other function. So in this case, it should be M is equal to C to the D mod N. Okay, so that's the formula. So we know that C is 13. D in this case is 3. So this is 13 to the 3. mod 15. Okay. And that should give you back, of course, 7, which is the original plain text message. Does this make sense, guys? That's essentially the approach. We're not going to be using a calculator for this. We're just going to code it in Python to double check the values. Any questions? All right, so that's the first one. First example. We've gone over it. Yeah, so that should be good. So now that we've done that one, we're going to do problem number 2. And in problem number 2, we're going to use slightly larger numbers. So it's going to be a more complete example. I believe this one is problem 2 of your assignment. So we'll also double check this one in Python. All right, so let's go ahead and do problem number 2. Okay. I'm just going to repeat the same exercise, but with different numbers. So let's do problem 2. Problem 2. Okay, so if you notice, the fact that you're doing something like x to the y, that operation creates really large numbers. Now imagine if that d is really large already, that's huge. Okay, so that's like the key insight of this equation, that operation x to the y with large numbers explodes, right? And we will actually see this when we implement Python, how it slows down. So the bigger we make that number, the more it actually slows down. Okay, so let's try problem number 2 here. Just kind of repeating the same thing. So I'm going to do step 1, select 2 prime numbers. In this case, more realistic, a little bit more realistic, although these would be insecure. So this is going to be P is 61 and Q is 53. Yeah, 53. Okay. So we calculate, so step number 2, and you can double check that these are prime numbers, right? If you want. We will have a function that just generates the prime number, so it's really nice that way. So the first step, we want to calculate n, right? So n is going to be what? 61 times 53, right? And that should be equal to 3,120. Okay. Then we're going to do step 3. That should be phi, which is 61 minus 1 times 53 minus 1, which is 60 times 52. And this is equal to, oh, actually, I have them inverted. This is the 3120. This number here, 61 times 53 is actually 3233. Everyone with me? So n is 3233, phi is 3120. Got it? Questions? All right. So now 3120, 3233. So now let's say that we have to pick E. Let's say that we have to pick E. Step 4. Okay, and we have 2 options. I have 2 options, 17 or 4001. which one of these two do I choose from what you know so far to be E? 17, why? Is greater than phi, right? So remember that rule of one less, no, E is greater than one and less than phi, right? And we have established phi is 3120, right? Obviously, like I said, this is going to be an algorithm. So, but yeah, that's kind of the idea. So we would select E to be 17. Okay, really great. So now we have our public key. Okay, so if I asked you, okay, can you give me the public key? Let's say this is Alice. For Alice at this point, so you should be able to say, well, her public key is what? N comma E, which is going to be 3 to 33, right? Yeah, 3 to 33. Okay. And this is the public key, comma E, which is 17. Do you guys see that? That's the public key. Okay. When you look at this public key in OpenSSL, it's not going to look like this. It just looks like hexadecimal. A lot of it is kind of like encoded in a specific way, as we will see a little, maybe next week. But there are commands in OpenSSL that can give you these parameters as well. And this is going to be critical for the scavenger hunt, when I'll give you probably the key in that OpenSSL format, and you have to convert it into the format that gives you these parameters. Okay. So yeah, so we've completed step 4. We have E. Now we have to calculate the parameters for D. So let's go ahead and do that. So we are going to, let's say step 5, I think. Now we have to select D. And so we just have to select a D that meets the condition E times D mod phi equal 1. Okay? So we've got E and phi. Phi was 3120 equal 1. This is mod. E was what? 17, I think. Yeah, 17. And then D is what we have to solve for. Okay? So we'll do this. Yeah, so it's like that. All right, so we'll solve this one in a sec, but let's just finish up the process. So let's say we perform the calculation here, and D would be equal to 2753. 2753. So that's your D that solves this equation. Okay, so now I have both the public and the private key for this, and hopefully you're going to see something very interesting. So I think this is for Alice. So we're going to say Alice pub was, N is 3233. And the E exponent is 17, right? But look at the private key now. The private key, it's going to be, remember, these are N and E, and over here it's N and D. So this N is the same, so 32, 33. But notice now that the D exponent is much larger than the E exponent. So this is going to be 2753. And that's just the nature of RSA, that you will notice that the private key is much larger than the public key. Okay? So imagine once you start using really large prime numbers, and I mean a prime number with 1024 right, bits or 2048. So these are large. They have to be pretty large. Okay, you see why now you do not want to encrypt your movie with RSA, right? And instead you want to encrypt that movie with XOR AES. So RSA is really just for the key exchange, okay? Because the key is small in relative terms when compared to encrypting a movie. All right, great. So this is a very correct example, like the simplest that we can make it probably. So now let's go ahead and do the encryption and decryption of some message. And then we're also going to do this operation. So the first one I want to do is show you how to do this. And some of you probably already know how to do this operation. But let's go ahead and move on to the encryption and decryption part of this process. So I'm going to do here, the message needs to be a number in this case, right? So it's going to be, my plain text message will be 65. All right, so my plain text message M is going to be 65. Okay, so now I'm going to proceed to encrypt this using the keys. So encrypt. Okay. So we already know the formula. So C equals M to the E mod, and was mod N. I believe where N is 3233. Mod N. Okay. So we can plug in the values. So M is 65 to the 17, right? 17. Mod N, which is 3233. And there you go. That's it. So you perform this calculation, and C should be, for this example, which is what you will corroborate with Python, the result should be 2790. Yeah, 2790. Got it? So that's your cipher. Okay, 2790. Yeah. All right. So now the process is to reverse this. Okay. So we're going to now do the decryption. So decrypt, I'm going to move the screen here. Here. All right. So we're going to do the decryption. Let's assume we're on the other side. And also remember, whenever you're doing this, you have to remember, am I Bob or Alice? Which key do I need to use? Am I using Alice's public key or my public key? All right, so that's why for that part of the problem, it's very important that you work with a partner. This is what I've seen over the years, is that students think they understand it when they do it by themselves, and then when they try to do it with a partner, they actually don't get it, right? So you get confused. So it's really important. That reminds me also that we will do one assignment where you have to demo the results. Okay, so that assignment is essentially using everything that we've learned in this class. And so you have to demo because of that reason, because I have to make sure that you guys actually understand, okay, I'm supposed to use the public key in this situation and the private key in this situation and so on. So it's just one assignment when we use PyCryptoDome. So that one will not focus on algorithms. It'll just focus on understanding which keys you're supposed to use and when. Okay, but that's coming up in a few weeks. All right, so now let's do the decryption part. So we're gonna decrypt. So decrypt. Okay, we have that. So this step, we know the formula already. So we are decrypting to M. So it's gonna be what? C, right? C as in Charlie, to the D mod N, right? So this, once I plug in the values here, it should just blow your mind, right? So take a look at these numbers. So this is going to be M equals, what is C? 2790 to the what? To the D where D is, well, 2753, right? So imagine doing this calculation, 2753. This is one of the reasons why I like doing this, because first of all, this is not secure. This is tiny. This is not even close to reality. So imagine that computation. You see that? But anyway, that's the security of it. And these have to be really large numbers for this to be secure and unbreakable. Okay? Because it's really hard to go from N to P and Q. It's very easy to go from P and Q to N. Super easy. But in reverse is very hard. It's a very hard problem. You probably know this from high school. It's called factorization, right? So you guys did this, I'm sure, before, and that's it. That's if you could do it. And that's where a quantum computer comes in. A quantum computer actually is designed to be able to do that really well, apparently. So that's one of the use cases, because we probably all know that quantum computers, at least currently, they can't solve every problem. They're only for very specific problems like this one of cryptography factorization. There's also something called quantum simulation, where they're essentially simulating things that are quantum. And chemistry is quantum, right? At some level, right? So they simulate molecules and things like that. But it's not necessarily for every problem so far, right? So now it is possible at some point some genius invents a new set of algorithms that uses quantum computers for everything. But for now. But anyway, there is an algorithm already. So the second a quantum computer is available, Shor's algorithm is almost guaranteed to break this, the factorization. Anyway, so let's finish this problem. Okay. So we have C2790. We know D, we had defined it before somewhere here, D 2753. So it's gonna be 2790 to the 2753 mod, and then N should be 3233. So as you can see, this is not something that you can compute by hand or with a calculator. We're gonna have to use Python for this one, but Python does it really well. All right, and then once you crunch these numbers, the M message should be the original one, which is 65. And so I believe this is problem number 2 of your homework assignment. You just have to implement this in Python and make sure that that is correct, that you get the exact same numbers. Any questions, guys? All right, good. So yeah, so I've skipped a few parts, obviously, on how to select E and D. That's going to happen, I think, in problem 3, where I have to introduce like a set of functions that will help us with this. Yeah, there's something that Euclidean something function and something else. We'll see that shortly. All right, so just making sure. Yeah, so we completed problem number 2, okay? This gives us, a way of generating public and private keys, also going from message to cipher, and then from cipher back to message, and the values should be the same. All right, now the next thing I do want to demo is how to do this computation here. So this operation is something very familiar to you, okay? And so we're just going to see how this works. I'm going to use the exact same numbers. It's the modulus operation, the remainder, if you will, right? If you remember that. So I'm going to use a different color here, probably blue. And I'm just going to show you the operation for this one. Okay. So essentially we have this formula. So D, E, mod B equal 1. So if we plug in the values, that's going to be, well, we don't know D, and then 17 mod 31, oops, 120 equal 1. So in the previous example, we solved that D is actually, oh, we have it here. D is 2753. So we can just plug that in. Obviously, we need a search algorithm for this, but that's going to be provided later. So now let's say that the search algorithm is trying different things, right? It's trying different numbers. It comes upon 2753. So it's going to plug it in into this formula, and it should have a match. So 3120 equal 1. So 2,753 times 17 is 46801. And then you just do the modulus operation, mod with 3120 equal 1. So that operation is something like this. It's just a division. So 46801 divided by 3120. Do you guys see that? And then you just look at the remainder of it. So this should be 1. So this is 3120, right? And that's what? That's 1560. This is 5. So I'm not going to make you do these calculations by hand. I'm not saying that at all. Most of it will be in Python or on the exam code, but I just, I want to illustrate where these numbers are coming from. So yeah, so 1560, and then the 1 comes down, and then now this should be 5. So this 5 times 3120 is 15,600. So as you can see, the remainder is 1, and that's it. That's it. So then this 1, you can plug it up here, and you say 1 equal 1. Like that. And that's it. So that's the operation, okay? So, but as, like I said, we're going to use an algorithm for this, and that code is already provided to you. All right, so we've completed this example, and we've completed this example. Yeah. All right, so I think, yeah, we're now ready to kind of look at this in Python. We might just do problem number 1 today, start with that, and then do the other problems on Thursday. And then I'll keep adding to this. I think the next thing we will cover next week is that whole GCD thing, the greatest common divisor. So so the definition of the greatest common divisor is that it's the largest positive integer that divides each of 2 integers. So we will need to look at that, but I'm going to save that for next week and just keep going from there. All right, yeah. So I think that's good as far as theory for today. And let's just dive into the lab and do the first, at least problem number 1 in Python, so that you guys can start to corroborate these numbers and have that too. So any questions before I switch over? All right, you guys got these notes, and I think they should be on the PDF also that I provided, so you should have that available. So let's switch over now. So I'm going to click stop sharing, and I'm going to switch back to the to Brightspace. So now we are ready to read through the problems, and the problems should be more familiar to you now. All right, so I'm going to go over here to RSA homework. All right. All right, so here we are. Let me move this. Okay. So let's take this is this week's lab. So problem number 1. Okay. Bob wants to communicate with Alice. He wants to send her a message M. Bob knows the public key of Alice, which is N, E. Now Bob encrypts the message M using Alice's public key. Bob converts this message into a number M. Using the number M, Bob now creates ciphertext C using the following equation, which is the one I gave you. Now Bob transmits the ciphertext C to Alice. Alice will receive the ciphertext from Bob. Alice uses her private key to decrypt the cipher text to get the original text. This is done using the equation given below, which is the one that I've already given to you in the lecture, where D is the private key of Alice. And this is something that you might see sometimes. People will say, oh, D is the private key or something like that. Remember, the private key is actually the D and the N, but it's more correct to refer to these as the exponent, like the private exponent. But yeah, here it's just stated like that. So where D is the private key of Alice and E is the public. Okay. The letter N is the product of P and Q, which we've already defined, which are randomly and independently selected large prime numbers such that P is not equal to Q. Okay. All right. So now this is what we're going to implement, assuming that M is 7, P is 5, Q is 3, and that the keys or the exponents are E3 and D3, which is the first example we did. Calculate the value of C, right? So to do that, you have to write a Python program that demonstrates how this works, okay? So that's what we're going to do now. We're going to switch. So we're going to solve problem 1 by switching over to the virtual machine. Then you can see, once I solve problem 1, you should be able to solve problem 2 easily. This is the one I just did also. So you can see here, it's the same value. So what is C given M and all these parameters? And then problem number 3 will be the following, which is the more complete one that we will start looking at on Thursday. Now that you have completed problem 2, try using a more advanced implementation. Because of the complexity of the RSA algorithm, some functions are provided to you. So I'm providing like GCD and all that so that you don't have to implement it on your own. So everything is provided in the code. That example is actually a really nice example of RSA, fully complete from scratch. So no libraries, nothing. It's got everything. So it's really nice in that regard. Because of the complexity of the RSA algorithm, some functions are provided to you. For this problem, you will need the source code that's on Brightspace. You need to write the generate keys function, and then you need to use all functions available to generate the prime numbers, generate the keys, and encrypt and decrypt the message. Right? So that'll be problem 3, and I'll help you. We'll do that one on Thursday. And then finally, as you can see, problem number 4, using the code from problem 3 plus any symmetric encryption approach, send a message to your partner and achieve confidentiality. Okay. This time you must exchange the symmetric key securely. Okay. So that's going to be the assignment for this this week, Thursday. All right. So I think we're ready now. So all we have to do is implement the problem number 1 in Python. So I'm going to start up the virtual machine. Where is that? Okay. And let's just start up the VM. And while it's starting, I'll just get ready here. Also, don't forget that you do have that problem, right, that you're still working on. I did add a version 4 also on GitHub of it. That's a little bit cleaner than what we did in class, but there's still something going on with the logic, right? If you remember, you're able to produce something. It's just that the logic is not fully done. Do you guys remember what I'm talking about, right? So the DES with the 5-stall network and CBC. So that's still your homework. Okay, let's see how you guys do with that one. All right. Did I not hit? No, it's fine. Could be a fun one. There's also a really great book about this thing of prime numbers. I think it's called the Riemann hypothesis. I highly recommend it if you're looking for something interesting. It's a popular science book, so it's not like a textbook or anything. But it's about the importance of prime numbers and how powerful they can be and mysterious. Anyway. Oh yeah, sorry.
Oh, sorry. I'm not seeing a Dropbox for the desk assignment.
Oh, there isn't one?
No.
Okay, I'll create one. Yeah, sorry. Yes.
Is it the deaths assignment that's due this week or the RSA assignment?
We're just starting the RSA, so this assignment would be due a week from Thursday.
Okay.
So so the desk with Feistel should be due this Thursday, right? Yes, go ahead, please.
Next will be.
I forgot about that. That's right. So next week is full break. So no class on Tuesday. So well, actually, I think it works out well because this lab, that problem 3, takes a while for me to go through the code and explain everything. So what I may do then, what we can do, so you have a valid point there. So we're starting RSA this week, but we're going to continue it next week. So what I can do is I can extend the deadline on the CBC and Feistel, right? The DES. So instead of having it be due this Thursday, it could be due a week from Thursday to give you more time. And that way, we're also working on RSA. Does that work for you guys? Yeah. So I'm going to give you one more week for that DES, right? So that you can, again, it's not a lot of code that you have to write. It's really just figure out the logic, okay? And take a look at that version 4 that I provided. It's a little bit cleaner. So yeah, so then the DES algorithm with CBC and Feistel is going to be due a week from Thursday. And then this RSA lab is going to be due in 2 weeks from Thursday. Okay? Any other questions? Yes, please.
I can't find any instructions for the desk homework either. Did you just want us to submit just a picture of it working on both ends like we did for the CBC one?
Yeah, so you mean like a Word document?
Yeah.
I'll create one. Yeah. All right, yeah. It's the same thing, but
Yeah.
well, in that one you don't have to work with a partner. I really just want you to solve it. So just focus
okay.
on that. But I'll create something. Yeah, sure. Good question. All right, so let's go ahead and do this one. Or if you want, actually, let's just do your Julian, right? Julian? Yeah. So let's do that request. So let's go to table of contents. And so XOR, symmetric encryption, and DES. So we did this one. This is just CBC, right? So you guys already submitted this, right? Yeah. Okay. So then you want for that last one, I'll add a new module. I'll just call it DES with Feistel and CBC. Okay, so I'll add this module here. Still technically before the exam, so I'm going to put it here. Okay, and so I'm just going to add the assignment. I'm going to give you so this is what? Same thing. So des. I'll start with homework. Des with Feistel and CBC, right? So it's gonna be due not the 9th, but the 16th, correct? Week from Thursday by 10 p.m. And I'm gonna leave it open until 16, so until the 19th, just a Sunday. Okay? So the code is here in the crypto. I'm gonna add the link. So cryptography, right? So I had talked about this block ciphers, and it should be des XOR. Yeah, so it's des for sure. So that des XOR number 3. All right, so you can take a look at this one. Right, this is what we did in class. Create blocks. Yeah. And so essentially the problem is how can I put this? Let's just say, given the code as discussed in class, um, improve the logic um, to implement a DES algorithm with Feistel and CBC. Does that make sense? Yeah, so that's essentially what you have to do. So you have to take this code and just kind of, I remember it works, so I know it works from beginning to end. It doesn't break or anything like that. The problem with it is that there's a logic issue, right? So I'll start maybe with that. So I'll provide the link, and I'll actually, instead of providing this, I may make an update, like I may create des XOR 4. So just be on the lookout for that. Especially if somebody emails me and says, hey, I found this issue, so then I might update something. Now, this one also includes an implementation of AES. This is what you guys did for the previous homework, which is your CBC XOR. Yeah, so and then I think this is just the XOR operation itself. So I'll provide this as the link. Okay, I'll just say link. Okay, so I'll just say using the code provided in the link below, implement a working version of the DES algorithm that uses a Feistel network and CBC. The code provided should run. No. Just give me a second. Okay, the code provided should run correctly, but has one or several logic errors that you must correct. Does this sound reasonable? Is it clear what you guys need to do? Yeah? All right, so using the code provided in the link below, implement a working version of the DES algorithm that uses a Feistel network and CBC. The code provided should run correctly, or runs correctly, but has one or several logic errors that you must correct. Got it? Any questions? All right. So that's it. That's all I'm asking you to do. No, you don't have to work with a partner or anything like that. Just solve, and this is a pure logic homework assignment. I want you guys to really try to think it through. Yeah, probably using that DES XOR 3 is the best approach, or if you see a latest version of it. Okay? All right, so let me hit save here. Okay. Yeah, so you can take it as a nice, it's a very it's a nice problem because it's a pure logic problem, right? So it's just figuring out how to do the things correctly. All right, and then on Thursday, so I think we're out of time. On Thursday, we will then start the RSA lab. So I'll start with problem number 1, but I'm not going to assign it until we come back from fall break. Got it? Any questions? All right, guys. So we'll stop here for today. I'll see you on Thursday.